thank you for all of those of you who are students that showed up here before 9 o'clock in the morning. I don't think in my life ever did that, when I was a student at least. So, since we have half an hour, that's the end of the banter, so let's start. I'm going to talk today about trends in the AI. So I'm sort of attached to AWS Science, so there's always multiples of tiers of things that we do. Some of the things are the bread and butter research that we do. Some of them are applicable research that trendy. Some of them are quite futuristic. So here I'm talking about a couple of things that have become in the recent 3 years or so become very prominent. The rest of them, we don't have time for it, but stay in tune because by the end of basically the Q1, I'm going to have a lot of material coming out of both reinforcement learning and causal inference to be published. So today we're going to take a look at AI explainability, some basic methods, a very rudimentary look, as well as looking at the graphs. Hopefully we have time for it. So explainable AI, you have heard it. The business schools are very keen on it. The philosophy departments are very keen on it. Therefore, there's a lot of mysticism around it and not a whole lot of material that actually matters. So first thing is trust. You have to be able to trust an algorithm the way that you trust a human. So if you don't know what the humans do, you have your defense mechanism is an evolutionary process. It makes you think there is some malignant activity behind the scenes of things that doesn't go your way. So you need to be able to trust the system, how it makes a decision. If your loan's been rejected, you're entitled to know why. There's transparency that is coming from, again, through transparency you gain trust. So how transparency works, as I said, you're entitled to know why your job application has been rejected. Then there is fairness. Data is biased, humans are biased. We're trying to train a system based on the actions of humanity, and therefore what the system learns is learning those biases as well as what it's supposed to do without those biases. So we can create fairness. We can create accountability by adhering to or complying with regulatory requirements. We can troubleshoot a model. A model doesn't work. We had it very recently I was consulting Amazon Logistics. We built a model that was basically given 53–54% accuracy. So we started looking at what it's doing underneath, and it helps us to fix the model. So that's quite important. You can do training, a lot of algorithm, a lot of on regular basis, outperform humans by a large margin. So you can show human, oh, this is how the machine made that decision. So that helps humans making better decisions. And as a result, the data becomes mutually reinforcing. So what is the history of explainable AI, or a need for AI explainability? In every field of science, what's been explained and the way it's been explained, they should be at the level of detail that actually makes sense. Let's say, if you want to talk about the properties of water, there is no point of looking at the subatomic particles like protons and neurons because they're all the same. They all have the same mass. They all have the same charge. They all have the same size. The proton in this atom is not the one from the other one. So that level of detail doesn't have the information constituency with what's been explained. So if you want to talk about the properties of water, then you have to go to the atomic or the molecular level. And if you don't, you end up with something like this. There's a very, very simple 3-layer network. So it does a text generator. So the way it works, so it's got an embedding layer, it's got a basically gated recurring unit, and it's got a dense layer. And that tiny little network's got over 4 million parameters, and it just printed some state of inside parameters, and that's what you see on the right. It helps to see, let's say, the distribution of the weights, which, the weights are not distributed, like in a Gaussian way, so it's not good. But it doesn't explain how the language works, right? So it doesn't explain why this word was detected to be a verb and the other one a noun. So the level of explanation here is inadequate. It's not understandable by humans. So as a result, what we want something that makes sense in terms of constituency information. So here there are two sentences, same sentence, been interpreted in two different ways through the understanding of the grammar. The other one, the one on the left, it says, I shot the elephant in my pajamas. So the way it's been interpreted could be the elephant that on your pajamas, the picture of the elephant on your pajamas, basically shot yourself in the foot. The right one, it says, I shot an elephant who had been wearing pajamas. So that's a very silly statement, but there are two different statements, right? So that's the level of explanation we want. So these two, they're no longer working on the basis of the values of the neurons and all of that. And what AI explainability is going to do is try to create that intuitive understanding of what happens inside the model. What goal do we have in here? At least in this context, we're trying to find, for AI explainability, a surrogate model. A surrogate model is a simpler model that behaves consistently the same way that the more complicated model works, but the simpler model is understandable. That's called a surrogate model. In this talk, we're looking only at the perturbation methods. There are other methods like the backpropagation methods. So the perturbation method combined with feature attribution is that we're going to chunk this, basically the input data in larger, basically superpixels in a way that they make sense to humans, and then we're going to turn them on and off and see how it affects basically the decisions been made. As a result of that, we can say, oh, that part of the picture or that part of a sentence resulted in that decision, so we can pinpoint the decision. And it already, basically the way I mentioned, that we're also looking only as that local or individual decisions. It's local explanation, so that's individual decision. That means you can go and say, why did you reject my loan? It's not about how the whole, basically, algorithm makes its decision. That would be global explanation. So let's see what is a local explanation. You go, you put a loan application, the system says rejection, then you telephone a person, why on earth did you reject my application? The system, the human doesn't know. The human is going to ask basically explainable AI, and explainable AI is going to talk back to the human, and then the human going to send you a diagram that says these are the parameters that were positively affecting, these are the ones negatively affecting. Let's say your income, the amount of debt you have, you know, that sort of stuff resulted negatively, but your age was a positive thing and that sort of thing, and that collectively we could not give you the loan, but these are the things we looked at. Apart from that, you can take a look at the bias in your own information. So if you've been rejected for a loan on the basis of where in the city you live, that's irrelevant, is it? So if you live in the suburbs of Paris, it doesn't make you financially worse off if you have the income and no debt. So you can also see if there is bias in here. Back in 2008, there was a study in Germany that people with Turkish and Arabic name that had a 50% smaller chance of being invited to the interviews. So that was humans, right? So, and then they did a lot of things to get rid of that bias. So the same thing we should do. In France, they did around the same time the same study, and it was the postcode. If you were from the suburbs, you were punished, right? And then the French tried to do a lot in order to get rid of those. And so what we have in here is understanding of the bias. Whether it's human or machine, we should be able to do that. Here is a sample implementation from the original paper method called LIME. So you see on the left side, you have an image, and then you chunk that image into superpixels, and then you're going to give superpixel by superpixel, let's say you have 50 of them, to the original algorithm, and it's going to make a prediction. I don't think that works, does it? No. So it's going to make a prediction for you, and that prediction is on the basis of probabilities of basically that it says it's a tree frog, but the probability on the top one is like 85%, and there's very little with the second chunk, and it's basically something with the third chunk. And then what LIME does in a local decision, it approximates your model to a linear model, explainable. So for that linear model, it uses the predictions you do for the chunks, for the superpixels, it uses them as label, and it trains a linear model that locally can explain what it does. How is linear? That try to imagine physics, like Newtonian physics. So the Earth is round, at least most of us agree, I hope, and then there's a ball, and you throw the ball. So since it's falling very near you, you can actually ignore the curvature of the Earth. But if you use a strong cannon, then you shoot it really, it goes and gets into the orbits and they start going, then you have to factor in the curvature of the Earth. So, result of that would be, if you can see things local enough, if you can deal with things, if you can basically have your view and local enough, you can always consider your space to be flat because the curvature is very small. And that's what Lime does. It tries to get these neighborhoods around the points that has been explained and take them as small enough, and that explanation could be done always through a linear model. That's what Lime does. It trains a linear surrogate model on the locality of the explanation, and that linear model is quite understandable, right? So that would be Lime. There's a different model. So actually, I have done in here, there's an example of Lime. They're basically family cheetah, baby cheetah, and a lion. And I am going to do prediction with, I'm going to do prediction with two different methods. One of them is Inception V3, the other one is ResNet 152. It makes some predictions, and after it does those predictions, it tells you is it cheetah, cheetah, lion, cheetah, cheetah, lion in the third one. The fourth one, it figures out it impala, and I'm coming back to that. So we have to be model agnostic, so I have used Lime library here, and then I did only 50 chunks, superpixels to be quick, and I did only 1,000 iterations, so that was very quickly done. But what it does, it tells you what region of the picture it has taken in both cases. Even though there are two different methods, there are two different algorithms that are very different, you see at the end that linear model is going around the same region. If I had played with that, if I had made my kernel a little wider, a little smaller, if I had done my chunks a little more, it probably would have had a much more accurate selection of the region. Was not necessary, but what we were trying to show here for the purpose of demonstration is that what we have in here is basically reasonably understandable by human why a lion is a lion, because we're looking at his bloody face. So not something in the background. So here there is a little piece of information. Where the hell did impala come from? So my idea was, maybe because of the environment is an African environment, it figures out it impala, and then try to predict a picture of impala and then put it there. It actually was quite good at that. Didn't need the environment. So that means I have not done a good thorough job of hyperparameter optimization for Lime. It has two hyperparameters. One is the width of your kernel. The other one is your complexity factor. The width of your kernel is because Lime, there's a method called kernel method. Kernel method is about reducing dimensionality. So that's what Lime uses in order to reduce your dimensionality to a linear model. So that Lime. There are other methods, which I haven't mentioned in here, like SHAP. Kernel SHAP is basically SHAP is very quickly is about feature attribution, is about how much every participant basically affects the result. So it lends itself really well to AI explainability through feature attribution. The good thing about SHAP is there are three different conditions. If they're met, it has an equation with a unique basically solution for that. That uniqueness is very good. So if you use kernel SHAP, it turns into Lime. I haven't got kernel SHAP in here, unfortunately. I removed them simply because we haven't got enough time for the half an hour that we're going through. Let's take a look at graphs, the second one. What we should care. Most real-world data doesn't fit in. All of that thing that we do, the data, it's just actually the world is not really flat, is it? So since it ain't, the data that we have about most of the problems that we solve are not going to fit in the real world. Let's say we live in a three-dimensional world. When we go to the cinema, we see a projection of that three-dimensional world into a two-dimensional space which has some illusion of depth. And that's what computer vision does. How about modeling the proper 3D environment? So that would be a graph, because things have basically multiple ways of connecting and not just a grid formation. So that's a tabular and sequential data. This is pretty much all we can do with deep learning. So they're either tabular in a way that on the left side you have the image, you have the RGB channels and a grid. On the right side you have the sequential data, and that's about all you can do with deep learning. Now I'm giving you a scenario here to see how much information is there in a seemingly simple scenario in here. Mary and Tom are siblings that they both are vegetarians. They like potato, they like cheese. Mary and Tom, they both work at Amazon. Joe is a bloke who is a colleague of Tom. To make the matter complicated, Joe loves Mary, but we do not know if the feeling is reciprocated. So they're all relationships, right? Some of them, Mary and Joe are siblings. It goes both ways, it's symmetrical. But Tom loves Mary, we don't know if the opposite is correct, if it holds. See, all of them are very, very complicated relationships that have to be somehow modeled. Joe is from Quebec. He's proud of his native dish of poutine, which is composed of potato, cheese, and gravy. We also know that gravy contains meat in some form. So if Joe is going to have a little dinner invitation and is trying to invite his friend Tom and trying to get Mary to come in as well, and then he makes them poutine and he's doomed. So it's very normal for us to know that he shouldn't be making poutine for the vegetarians, but how does the machine know that? Can we put all of the information of the world into an algorithm and make it a decision? Or we have all of that partial information and we're going to complete that information somehow that you infer from those, all of that multidimensional ways, all of those things that your relationships are different. You have employee, you have colleague, you have sibling, you have liking something. All of that are too complicated. There's so many different one of them. And then there's different levels of them. How much do they like potato? A lot? Very little? Can you quantify that? So when you look at all of those different types, and then there are different things. So let me walk you through an example. So actually I'm going to, let's say Amazon is an entity. It's got a company registration number, HQ location. Tom is a human being. It's got height, it's got language, it's got address, it's got friends. So when you look at all of that, every entity has such massively different properties to take care of. So you can't put it in a table, can you? So unless this table is going to have infinite number of columns that are infinitely empty, which is not going to work. So then we need a different data structure. So we use graph data structures for things, for every time that the entities are different, or the connections are different, or they're both different. At that point, you're out of basically anything that the tabular data or image data or any of these two-dimensional data, Euclidean data, if you will, could give you. So social medial data, molecular data. We have done some drug research in the beginning of COVID. Citation networks, all of that are examples that you can use graphs. So there are some examples from standard. There's a very nice course in Stanford if you want to take a look at it. So let's say the 3D shapes we already mentioned. The social networks are very obvious. The molecules, what you have that is important here, you see there are just the ones with the two bindings and one binding. So there are different connections that you can have. So all of that data comes to graph. Basically, the graphs are created an expanding universe of deep learning for us that we did not have in the past. So examples, node classification, predicting the property of a node. So the same old recommendation based on users and items could be actually done. I'm going to give you a good example of that, I hope. There's link prediction to see if there's a relationship between something or not. So let's say if you want to see Mary works at Amazon, Tom works at Amazon, Joe works at Amazon, so there are different links we can predict. It's called the employee relationship between Amazon and these people. Between them, we can predict colleague relationships, so they're colleagues. So something you can actually predict, that's called a link prediction. So there's graph classification. So a whole graph or a subgraph can be classified. Let's say The case of medicine. So usually, if the molecule of your medicine has a very isolated corner that is got really tightly bound together, but has a very, very, very basically just a single link or a double link to the rest of the molecule, and has a certain formation that indicates toxicity. That's a bad drug. You shouldn't be basically wasting your money doing chemical research on that. That's a toxic drug. So that usually indicator of that. So if you can do subgraph classification, and then you see this subgraph of you as a toxic subgraph because it has similarity, structural similarity to toxins, so that's a bad drug. Don't waste your money. That's your pharmaceutical money. You can use it to give somebody some sort of basically extra salary. So, and then you can use it for clustering. So if nodes are a community. So let's say, how do you do that? For nodes being a community, you can do, let's say if some people could be introduced to one another. So when COVID came in, we were trying to see how do we deal with this remote conferences. It came from an internal conference we have in Amazon. So there are thousands of scientists in the company, and then we have this annual huge conference, and then we couldn't go there. So we started thinking about how to do that. One of the things they had, it was linking people together that might have similar interests. Something you do at the water cooler. You come here, you talk to someone, you socialize. Oh, you work in that field. That's very nice. I work on the same field. Or I'm interested in what you do. Let's talk. So we worked on something, called it jokingly brain dating. So the whole thing was to figure out if people, based on their previous publication and this and that, should be put in contact in order to be able to, you know, like, might be interested in somebody else's work. So this is called clustering to see if a social circle can be detected. So other things like knowledge graph embedding as the next thing. So the knowledge graph embedding, we already looked at the life of Mary, right? So the world of Mary, we have seen some very basic relationship. That's a knowledge graph. So a knowledge graph is all of these semantic relationship, many of them missing. So how do we complete the, you know, how do we tell Joe, I think he was, don't give them poutine? So how do we know that they don't like poutine? So this is the knowledge graph embedding. So you have partial information that has a lot of hidden semantic information in it, and then completing that graph using a graph neural networks is called knowledge graph embedding. It's a very, very, very detailed and very, very nice way of doing that. So I've written extensively about the technical details. Sadly, we cannot go through that, but I can give you references afterwards to read. So another example of knowledge graph embedding that is a little more mundane than trying to find drugs, you know, medicine, not those drugs. So here's an example. Look at that. There's a user M1. It's got no tags at the moment. There is a book, B1, and that book has a tag called environment. It's a book about environment. If that user M1 interacts with enough objects with the tag environment, we can tag that user as somebody who's interested in the environment. Then, there are other products, such as washing machines. They do have tags. They have they have different tags. Like, for instance, they're energy efficient or not so energy efficient. So there is A+, or there is C. So something that is energy efficient has a semantic relationship with books that are about environment. So this chap, user, is going to buy a new washing machine, and then which one would we suggest to him? Like, we're humans, we simply can just common sense, oh, tell him the one that is environmentally friendly, because he seems to be a person interested in the environment. So, but doing all of that is basically building a knowledge graph, basically building a mechanism, building a system around it using graphs that actually predicts all of these links. So a successful system is the one that is going to basically make this basically environmentally friendly washing machine on the top of the list, and the rest of the list would be something else. So because probably that person is not that bothered about like 50 euros more for energy efficiency. He probably drinks organic coffee as well. So drug repurposing, that's another one. That's a project we did. When COVID hit, so one thing we did was we did a paper on figuring out, based on the genetic signature of COVID virus, and the medicine that was available in there, basically the molecular structure of those, we managed to basically create a short list of the medication that could have been potentially working for COVID. This is not definitive. You give that to the doctors, and then they can focus on a much narrower spectrum of research in a shorter period of time. So that is coming from that research. So virus has a genetic signature that is core of the graph. And then using the knowledge graph, we can create a graph that basically looks at all of these different, other information to that genetic signature. And then we discover, then we do something like a, graph clustering or graph, prediction, the whole graph of subgraph prediction, and we can come up with a list of drugs that exist that can be repurposed. So what have we done in the open source universe for these things? So as a part of AWS Science team, we have created DeepGraph library. It's a Python package built for distributed graph neural networks. It's quite fast. It works in CPU and GPU. And it's got a huge number of tutorials based on the functions. So there's a getting started tutorials. You can actually find that in the product page. It's open source product. And more importantly, it's got examples. There's a huge number of papers that have been published. We have taken those papers and we have implemented them. And then you can find them basically when you go to that link. You can go and see, I want to do collaborative filtering, I want to do clustering, I want to do bipartite graph, whatever it is that you want to do. Then you click on it, and it takes you to the GitHub library where the implementation is, and you can start adopting that implementation. So it's not just science, it's a lot of code and examples. There's another product called the DGLKE that we used it for the drug repurposing. So we have created basically a super fast product that does distributed, sitting on top of DGL, does a lot of distribution, and basically completes your graph knowledge embedding and creates knowledge graphs for you. The architecture of that basically is on the top, there are different papers. There are different ways of doing knowledge graph embedding. So in one of the links I have at the end, I have done a review paper of all of those 6 methods that you see on top. So trans, E, trans, R, rotate, E. So there are methods that you do knowledge graph embedding. On the top, basically, they're sitting on top. Below that, there is basically the DGL and those products that we have used to implement those methods. And then below that is CPUs and GPUs and clusters and whatever it is that you do. But most of the sciencey bit is on those blue squares. The comparison for the speed. So comparing with GraphWhite, you can see the pink is us, the blue is GraphWhite. When you do it on a single GPU, you see there's a massive optimization on distribution, even on a single GPU. When you distributed multiple GPUs, it's still going almost linearly down. And then there are different methods, like trans-E, dismult, complex, and rotate. So like it's really difficult to say what they are now. I refer you to the reading of that review that I have written and is linked to that. So it goes and explains details of every single one of these methods. And the second one is basically, that was a runtime. The second one is the training methods. Basically, you can see that at the same time. DGLKE on 4 machines is basically the performance, the red one. It shows you how quick it is. That means it's cheap to operate because GPUs cost a lot of money. So when you see those things, that means if you want to do implementation, so you can consider the cost of using DGLKE would be quite substantially less. So other areas of importance, that are the coming. So I will have a series on reinforcement learning. Reinforcement learning has been going in and out of attention for so long now. So I think I have been in 2, 3 different waves of it in my own lifetime. The problem is we cannot figure out the simulation, because they need a simulation of the world. Like, nobody seems to be able to figure them out outside of computer games or the game of, what is it that Google made? Not checkers, the other one, forgot. Game of Go, I think. So, we seem to be not to be able to basically build those simulators of real world outside of computer games. Still, everybody is just hacking at it. One day it will come, and that would be nice. The way the reinforcement learning works, unlike anything else, it interacts with an environment and it learns from experience as it runs. So it's a lot more similar to biological learning than everything else that we do. So that would be brilliant if we can simulate the bloody world. So the other one is causal inference. It's not a new field, but nobody seems to be interested in it. All machine learning is about association, not causation. We don't know what causes what. We just know, to tell you, like my grandparents used to say, when the jays come, the spring comes. So is that the bird bringing the spring or the spring bringing the bird? For us, it's quite simple. For a machine, it's very difficult, right? So causal inference, we have a team in University of Tübingen, and they're very, very, very advanced, and I'll start working with them in the beginning of the new year. So hopefully by the mid next year, there would be a lot of material implementation of scientific things coming out. So this, what we have in here, is the causal inference. Basically, court orders the shooting, like the chain of responsibility. This also is done through directed graphs. So the graphs are important once more. The second thing that I've done a lot of talks this year, and I have in a conference in Munich, we were talking about it with some of the science group as well. This is AutoML. We do have an open source AutoML product. It's called AutoGluon, that does tabular prediction, image prediction, object detection, text prediction, bimodal, and time series. Basically, you give it raw data, it gives you a machine learning model. So if you know nothing about it. And if you know about it, so you can do better. References, I leave them on references. I have 31 seconds for questions, apparently. Sorry. Questions? It's always a good sign. I've done a fantastic job of confusing everyone. Right then, cheerio.